first two approaches just showing you that how difficult this calculation can be. Not difficult, but long, calculation can be. And third one, they use this trick because it's a very special example. So they start with this sphere, x squared plus y squared equals 1. And this is basically a plane, but as soon as you put the inequality there, it means the solid region. So x plus y plus z equals 1 is this plane, which is actually the infinite plane cut out by this box so that it looks like a triangle, but it's infinite plane. And this infinite plane divides this xyz plane in two different regions, right? To this right side of this orange plane, to the left side of this orange plane, right? So this one corresponds to the right side of the orange plane. You can do that by trying some point over there, like 2, 2, 2. Does that belong here? 2, 2, 2 is greater than 1. So anything to that side, because they satisfy this inequality, therefore it belongs to this side. If you try 0, 0, 0, down there 0, 0, 0, it does not satisfy. So this one is less than 1 region, stuff like that. So here's a sphere, which is different from solid ball, right? Ball includes all the points inside the sphere, and the sphere means just the points on the on the surface there. And cut it out by this inequality means we're including all this cut of the sphere, right? And then it creates this boundary, and I'm going to use a dotted line there. I hope you see that. So that's our surface. So if this is our surface S, you see the boundary, right? Boundary is this one, correct? So if I go around like this, can you use your right hand rule? So how this surface S should be parametrized, the oriented. So two direction, either is sticking out from the interior of the sphere or sticking inside interior of the sphere. If you use right hand rule, that one turn and go around like this. This is your four fingers pointing that direction, your thumb is pointing outward from the interior. Agree? Yeah. So if it's oriented like that, is outside, oriented inside, you have to go around like this. This only make the difference of plus minus, right? So they ask you to compute this surface integral. What's inside the surface integral? This is what of f? Not the gradient. It's a curl of, it's a cross product, it's a curl of vector field f. So this has interesting property. What is that property called? This vector field, curl of f, has this independence property, right? What is that independence property called? Surface independence. Doesn't matter which surface you choose, as long as you keep the boundary, this integral will be the same, right? Or you can use the Stoke's theorem, just line integral around this circle hovering like this in the space. That will be the answer. So we have two things going on. If I call that surface C, not the curve C, we have curve C of vector field f dotted with dr. This is line integral, right? Is equal to the surface S we are looking at with a curl of the vector field f dotted with normal vector of whatever the direction you choose and the surface integral, right? So that's the question. Compute this one, right? And then you might think, oh, maybe I'm going to compute that one, right? Because the seems like parameterizing surface is really hard. Actually, it is hard. I don't think the book even does do that. But it is possible because the sphere and plane, doing all sorts of completing the square and all that, it's possible to surface S. It's a whole lot of work. It might fill up the entire page just to parameterize it correctly. Then you switch to here. Maybe you're going to do this, right? Because parameterizing the surface is too much work. How about parameterizing the circle hovering in there? That's also a lot of work. Relatively, smaller work than the parameterizing S. This is still a lot of work. Okay? So the book explains that. You have to find the center of this circle that is on that plane. And you have to figure out one vector and its perpendicular vector. And then you have to use a sine and cosine. Parameterize all that. And then go back and plug it in here, your formula of f in there, and do the line integral. The parameterization of C is still a lot of work. Relatively smaller work than parameterizing S. So both ways seems like involves a lot of work. Now it's introducing the third option. Because this is special, it doesn't always work. Third option is that using the surface independence. What the surface independence means, you come up with a new surface, right? S1, which is easier to parameterize than S, and you do actually surface integral rather than going to line integral. So what surface, S1, which shares the boundary, is easier to parameterize? S is this part of the sphere, right? What should we do to simplify this one and it's easier to parameterize? Is the surface independence, right? Yeah. Right, you must have a boundary. You can't change the boundary, but you can change the inside the surface. Yes. I don't know. So we have to keep this boundary circle there, right? We have to change that S to simpler one to parameterize. I don't know. Yeah, that seems like the best one. Just shrink down to the plane, right? Easiest to, parameterizing the plane is the easiest thing, right? Modular parameterization. Does that make sense? So think about this disk that is perfectly part of the plane, flat, versus this one in here, actually the hemisphere, the surface there. Parameterizing this one's hard. Parameterizing this one seems easy, right? It's on that circle. Make sense? Still, actually parameterizing this one, it still involves work, a little bit of work, but it is still less work than these two. It's getting down a bit better and better. This is even simpler than it turns out. It turns out if you calculate F was, I think it was y minus, this is x, y, z, that's z, r, that's position vector, cross with I, j, k, the expression is like a different way. If you calculate this cross product, the vector field we're looking at is, I think it was this z minus x, or x minus y, something like that. I think I did it correctly. So I skipped that calculation. If you do expand this one, that's the vector field we started with. We're calculating this one, right, with S1 being this flat surface, with the boundary still same as that circle. Okay? So this equality makes sense? Seems like we're going for this one. Okay? So what is a curl? You do this calculation. There, right? And it turns out it's all -2, -2, and -2. So let's try this part. If you do the cross product, it is -1 as you cross that. And this one is +1, but the minus BC is this -1, -1, -2, right? Fair enough? Yeah. So if that's -2, and if you know what the direction of this vector is, this plane vector, which is the normal vectors for S1, which is part of this plane, right? What is this normal vector of this plane? 1, 1, 1, right? If this is -2, better be -2, -2, -2, which you will verify by calculating the curl as well. But this should coincide with this plane because we chose S1 instead of actual S. Make sense? So what kind of vector field is this? It does not involve any variable at all, right? So it's a constant vector field. This is how we start the surface integral. The very first example of surface integral I gave you is a constant vector field that's going upward like that, right? And then I interpret this one as a fluid density vector, right? Fluid density vector. Meaning of that is that if you, this and that is the same direction, it turns out. That's a curl F. And if you sample tiny region, like said delta A, multiplied by the magnitude of curl F, in general this should be curl of F, what with the general scalar density, the normal vector of this one, dot divided by the length of this is orthogonal projection. So if it is all constant here, then that much of the particles going through per square inch. So if you multiply that area there, that's the number of particle for that small square inch, right? And we don't have to integrate because it's constant all over the place, right? So from there, what is the number of a particle that passing through this entire circular region? Is the area of this entire circular region, right? Times, yeah, this whole thing. But it has to be this one. The well, that n here is 111. How about that? Is that okay? And that's the direction of this plane, and the curl is happen to be that. Yes. Right? So that means surface integral over this part plus surface integral down that part together with a 0. So if I call that one A1 and A2, that's a 0, right? So if you want to calculate A2, you can calculate just A1, its opposite sign. That explains the surface independence. So what you're thinking is that surface independence is explained in some other way. Surface independence means if you do the closed surface integral, that whole thing is going to be 0, right? So if you want to calculate one piece of it, it's the same as calculating the other piece of it because they together become 0. So it's the same as calculating this one instead of that one, right? So that closed surface is actually a part of surface independence explanation. Good observation. That's correct. Anything else? All right. So the area of the circle, which we'll calculate later, and what is curl? -2, -2, -2, right? And what is this normal vector of this plane? 1, 1, 1, right? Or you can choose -2, -2, -2 as well. That's a normal vector too, right? Because it's perpendicular. But I can change the problem slightly so the curl is not the same direction, it's a slightly different direction, but constant, right? Then you better use this formulation. So what is the length of this one? √3. So, right, this 111 is a √3. That's the length of that one. So all you have to compute is the area of the circle and you're done. Does that make sense? Yeah. So it's a special case. So how do you calculate area of the circle? It's if I know a center and one point that this intersection of a plane and the sphere is passing through, then we can calculate that length in between. Or if you remember distance from the plane formula, if you have a point here 0, 0, 0, right? That's the center of the sphere. Go straight perpendicular to the center of the circle, and if you know that distance, and here when you go around like this, that's the sphere, the radius of the sphere, so it's 1, so you can use Pythagorean theorem to do that. There are two ways to do that, but point seems like easier, so I'll go for that. So we have to calculate the center of the circle. The center of the circle, hope you believe that if that's center of the circle, and that's a 0, 0, 0, and if you pass through like that, that vector here is equal to the normal vector of a plane. Does that make sense? Yeah. So if that's 1, 1, 1 direction, what do you think the equation of the line is? Right, is x equals y equals z. That all has to be the same if it's the direction. If you think about equation, starting from here, this is 1, 1, 1 direction, so the 0, 0, 0 plus t times the direction vector 1, 1, 1, right? It's 1, 1, 1. So that's the equation of the line. X equals t, y equals t, z equals t. That's this line equation. When does that meet? That plane there, this plane equation, is x plus y plus z equals 1, right? So if you plug it in there, is t plus t plus t plus equals 1. So t is 1/3, right? So that point there is 1/3, comma 1/3, comma 1/3. All right. So if I go try it again, so we got that point going to call P. All I have to go figure out is one more point out there on the circle, which is part of x squared plus y squared equal plus z squared equals 1, and x plus y plus z equals 1. That's where these two surfaces intersect around the circle, right? Down there's a 0, 0, 0. If I can come up with one point out there, I can do the distance formula. So by looking at this equation, solving this equation for x and y and z, there are infinitely many solutions. Can you come up with, by inspection, very simple solution that is satisfying this one and this one at the same time? 0, 0, 1. That seems like a simple one, right? So 0, 0, 1, by plugging in here, you clearly see that that's on the circle because it's on the sphere, it's on the plane. And what is the P there? This is going to be Q. That's point Q. My point P was 1/3, 1/3, 1/3, right? The distance between R is going to be part of this area, correct? But the area here is at pi r squared, so we only need r squared. It's distance squared, right? So let's do that. Pi times r here is this 2 point, that 2 points. What is the distance between these two? 0 minus is 2 over 9, is that right? If you square it, and that's 2 over 9, squared this one, is that 4 over 9? That's what it is, right? 1 minus a 2 over 3, if you square 4 over 9. So I claim this is r squared, the distance between these two. So pi r squared, that's the area of the circle. So altogether, what is it? 8 over 9? Pi, that's the area of the circle. Let's go back to the integral, that integral over that flat surface of the curl of f dA. Now interpret this area times this orthogonal projection of a constant fluid density vector, right? So what is this one altogether? It's negative 8 divided by root 3. Did I have this right? Negative 6, not 8. So they cancel a bit, giving you the whatever number. So 2 is a 16, you think? Divided by 3. If I did this right. Which part? Is that right? It's negative 4. Negative 4 pi over root 3. Is that right? Okay, thanks. Well, that's a very special example that you don't usually compute surface inequality this way, but it all became like this because this was a constant density vector. Then just area times the orthogonal projection is the area, is the surface integral. All right?